When valuing a financial derivative, have you ever wondered why you would actually use Monte Carlo simulation? What is Monte Carlo simulation? What is the risk-neutral pricing, the mathematics behind Monte Carlo simulation? How can we actually rely on this method? What benefits is there over other valuation methods for financial contracts? And why is it that a stock growth rate actually doesn't enter into the derivative model? Now, we're going to be answering all these questions in this video. We're going to be delving into the financial mathematics behind these concepts, and we're going to be going through it step by step. So stick around. So we're going to be making our way through these slides here. I promise they're pretty streamlined, and we're going to be asking questions throughout the way. The math is going to be quite simple. So what is risk-neutral pricing? Well, essentially all it is an option value is the discounted expectation of its future payoffs. So what are we trying to say by that? We're trying to say that every kind of derivative has a payoff, and if you take the expectation of all those price parts and discount them back to the present time, that is the value of your option. So questions that we actually have about this risk-neutral pricing methodology: why doesn't the underlying stock growth rate impact the option price? Doesn't show up in the Black-Scholes formula or other derivative methodologies. So why would we use this over replication and methods for solving PDEs? What are the benefits of the risk-neutral pricing approach versus replication and solving the PDE? So let's look at the motivation why. So let's answer the first question. Does the underlying stock growth matter? The answer is no. And the reason is because we're actually exploiting this characteristic of the derivative and the underlying, that there is a perfect correlation between the two. If the only random variable is the underlying that we're trying to value, then it is in fact a perfect correlation. So by exploiting this, let's just imagine that an option increases in value with a rise in the underlying price, for example, a long call option. So if we have long one option contract, then we can replicate this payoff by being short a number of units in the underlying. And what that does is that we essentially create a risk-free portfolio by exploiting the perfect correlation between the change in the value of the option and the underlying. So what we can actually do, we can actually eliminate risk. We're not valuing risk because essentially the derivative is it has a perfect relationship with the stock, and therefore what you actually get is during that time of the life of the option, if you were to perfectly hedge the entire way, you end up getting a payoff that looks a lot like a bond. So why use the risk-neutral pricing formulation? Well, essentially there are quite a few benefits, but essentially with realistic derivative formulations, there can be no closed form solution. So multi-dimensional models with very complex payoff structures and complex contract features, it can be very hard to actually use the replication and then solve a PDE. So the second reason why we'd actually want to lean towards this risk-neutral pricing methodology is because the replication approach and then having to solve a PDE in high dimensions is very computationally expensive. Now, the risk-neutral path methodology, when you actually take this discounted risk-neutral paths and you actually simulate that out, by taking the expectation, we can actually easily approximate the option value using Monte Carlo, and this is less computationally expensive than having to solve high-dimensional PDEs. So I want to take things back now. We're going to consider the one-period binomial model to start off this risk-neutral pricing discussion. We're going to have our probability space, as you can see in the top left-hand corner. So remember, we have the stock at time 0, and there are two options in the binomial model. Yeah, the stock goes up or the stock goes down. And because of that, we have two different payoffs for the call going up or the call going down, or the option price going down. So remember that we're trying to replicate the payoff by using a portfolio of bank account and stock. So we have alpha units of bank account and beta of the stock. So our portfolio is just denoted by theta there. So remember, we're going to use the no arbitrage rules. So we're going to have the probability of the portfolio value of our stock and bank account is equal to the option value at time t with probability 1. Okay, so no arbitrage demands this principle. If we have the same payoff at the end, then we can say that these portfolio values are the same at time 0. So what we do is we just construct two equations, one with the up state and one with the down state. Now, no arbitrage demands, as we've just said, that the options value portfolio at time 0 are both equal to the same. If they have the same payoff at time t, then they have to be equal to the same value at time 0. So we exploit this and we say, well, our call price at time 0 has to be equal to alpha units of the bank and then beta units of the share price. Now, of course, our bank at time 0 is just 1 unit. So what you can do is you can solve those two linear equations and then add them into the formula, the alpha and beta. And what you can do is rearrange it so you actually get this formula here in the yellow, which is really just looking like a discounted expectation. So we have QU there, which is representing the risk-neutral probability of it going up, and then QD, or 1 minus QU, is the risk-neutral probability of it going down. So we've got the discounted expectation of this binomial model. Now, what I want you to see here is that this QU has nothing to do with the actual physical probabilities of the stock price going up or down. So the expectation under new probability measure Q instead of our P that we had before is now the expectation, the discounted expectation of the future payoff of that option. That's what the call option is worth. So now if we just remember what the fundamental theorem of asset pricing is, no arbitrage pricing, there exists a probability measure Q, so some kind of measure Q that's equivalent to P. What we mean by equivalent is just that they have the same probability space and that all the probabilities, sets of outcomes are equal. So such that the discounted price of all tradable assets are martingales with respect to Q. So what do we mean by that? We mean that the expectation of the discounted prices of a particular asset that we're trying to model is equal to 0. Not equal to 0, is equal to the previous price that it was before. So that's what a martingale is. Now, we need to actually realize something quite interesting here. So if we go back to our one-period binomial model, we're going to take a look at the actual set of outcomes. So the set of outcomes are, we can go up or down. So that's what we've got omega up and omega down for. That's our outcome space. Now the physical probabilities here, so the physical probability of the up is equal to PU. Now that has to be greater than 0, otherwise we can have arbitrage in this portfolio. So the physical probability of outcome 2 is the probability of it going down, which is just 1 minus PU. So now if we imagine things in this new probability space, this risk-neutral probability space, what do we actually have to do to shift from this physical probability to this risk-neutral pricing world? Well, let's take a look at this left-hand corner. So now we have QU representing the risk-neutral probability of it going up. So what we've done here, we've actually just applied a factor to be able to create this risk-neutral pricing world. So here we've just multiplied by the physical probability and divided by the physical probability. Now remember that the physical probability is denoted by this physical probability measure with the up factor. So what we actually get is that this random factor, this risk-neutral derivative factor, actually, if you multiply that by the physical probability measure, you can actually translate it into the risk-neutral world space under this Q probability measure, and that's a very important distinction. So we can reweight this physical probability measure P by a random variable called the random derivative, and we can obtain this new physical probability measure space, which we're denoting by Q. Now this is a really important realization. Here you'll see it often denoted as Z, and it's just the difference between, it's the derivative of the new probability measured by the old probability measure. So what we're trying to do, we're just trying to work out what this new shift is, what this actual derivative is that we can translate to our risk-neutral probability world. We're going from real world probabilities and we're reweighting it by a certain ratio, a certain factor to get into the risk-neutral space. And that means we can take this call value that we had in the discounted expectation of payoffs under the risk-neutral pricing, and we can actually shift that to get the physical probability expectation. So this change of measure is really useful. So now the objective for risk-neutral pricing, we need to identify this random derivative process, ZT, And we need to ensure that it's a positive martingale with an expectation of 1. So what do we mean by that? We need to identify a martingale process. So ZT obviously depends on our chosen model, but our objective is to find a measure that all the discounted stock prices or random variable processes are actually a martingale process. So the expectation today, the expectation for tomorrow is the same value as it is today. So that's very important. Now let's talk about geometric Brownian motion. We actually have the model for geometric Brownian motion here. So non-dividend paying stock has this formula here. So we've got a deterministic component and we've obviously got that volatility time value component. So in the money market or the bank account, that's actually modeled by a rate of change of the bank account, which is proportional to the risk-free rate R. So this is the well-known geometric Brownian motion. And what we're going to see is we're going to look at the dynamics here. So this Wiener process that we have here, the Brownian motion, is the Brownian motion under the physical probability space. When we state this model, we're talking about the physical probability in the P measure. But ST is very important to understand that it's not a martingale under the physical probabilities. Why? Because the definition is actually in the model itself. We have this deterministic component with a mu, and it's because mu ST is a non-zero factor. So we have this deterministic component, and by definition that cannot be a martingale with the same expectation from time step to time step. So what we can do is we can perform a change of measure so that we get this this new Brownian motion under the Q measure, which is denoted here by that W squiggly line, W tilde, and that's a Brownian motion under the new probability measure Q. Now that's very important. How do we identify that? Well, that's the Randon Nikodym derivative that we actually have to identify. Now we get into the most important theorem in risk-neutral pricing, and that is Girsonov's theorem. So the change of measure from a real-world probability P to a risk-neutral world that we need to value our derivatives in, so Q. So I'm going to put this in the perspective of the top right-hand corner. We've got an outcome, filtration, and it's an adapted process of our random variable, and we're in the physical probability space. So we're going to imagine that we have this process alpha, and it's going to be adapted filtration Ito process, so that when the Q measure is an equivalent measure on the outcome space, such that we have this new Brownian motion that is a martingale process. So what do we mean by that? We mean that under the physical probability, remember WT is not a Brownian motion, because it's not a normal, it's not a normal distribution, because we have that deterministic process of mu st. Whereas we're actually trying to identify this process alpha with respect to time, so we can actually make a translation, a shift in this Brownian motion, such that the Brownian motion in the risk-neutral world is normally distributed and therefore a martingale process. So there's one really important condition, the Novikov condition, and all this is required because we need to ensure that that Randon derivative is actually a martingale. So that's just this complex expectation here over the time period that you can see. That means just that the squared of the actual Randon derivative and the multiplied by that process squared is actually finite. So that's a very important statement, and it's required just to ensure that this ZT process is actually a martingale. So let's now, that was very theoretical. Let's actually apply this so you can start understanding geometric Brownian motion a little bit more. So let's go back to those dynamics that we've just laid out for the stock and the bank account, and we're going to try and shift things from the physical probability to the risk-neutral world. So the objective is to find this Randon Nikodym derivative that removes the drift term, so that the stock dynamics are now a martingale under this new measure. So now, I'm cheating a little bit here, but we've set it in the derivative, we've set it in the actual definition of the first fundamental theorem, and that is that the discounted stock process is a martingale. So the discount is just simply the stock dynamics divided by the actual bank money market dynamics, so under the GBM model. So I'm being a bit sneaky here, we know what it is, but for more complex processes and when you try and increase the complexity of these SDEs to model more realistic scenarios, it's not as simple to find out what this is. But here we're going to look at the process of this new measure, ST divided by BT. So the discounted stock process is a Q martingale, and we know that from the first fundamental theorem. So to actually prove that, let's take a look at the dynamics, and we're going to use Ito calculus here. So what are the dynamics, the changes that we can occur with this model, new model, ST over BT? So we're going to look at the change in ST, which we've already got defined, and we're going to now compare that to the changes in 1 over BT. Now we're going to use Ito calculus, which remember we can identify if we're looking at the dynamics of different STEs combined together. That's what Ito calculus is there for. So let's take a look. So our new dynamics are, just using Ito calculus, we've got ST times by the dynamics of 1 over BT plus 1 over BT times by the dynamics of ST plus a half. Just remember the Taylor expansion formula there of the dynamics of ST over the dynamics of 1 over BT. Now what we're going to do is we're going to substitute these dynamics into that equation and rearrange. So what we're going to do, we're first just going to place the dynamics of 1 over BT, and we're going to leave dST there because it's a bit complicated to rearrange them all at once. So you can see we've got that minus RST over BT dt. Now I'm already looking for factors that I can take out. So before I substitute everything in, I'm just going to take out this dST term. You can see that I've factorized that out, and now I can see quite clearly that I have some cross terms that I can get rid of. Remember in our Ito calculus that cross terms of dt and dt approach 0, and the same with dt and dw. So we can actually cross out that entire term there that I have in yellow on the left-hand side in the factorization, but that's still going to cross multiply to the 1 over bt. So if you take that one step further, what you get, if you factorize out by the volatility and then ST over BT factor, you get this, this relationship or this transformation of the Wiener process by this deterministic term. Now, this is our new Brownian motion. So the translation to the old physical probability Brownian motion is by this, what's called the market risk factor. So this mu minus R over volatility, and that's now a deterministic shift. So what do I mean by that? I mean now, here looking at the new formula, you can see that if we just substitute our new new Brownian motion into the formula, we actually get something that has no deterministic term. This is now just a normal distribution of this process ST over BT. So we have no drift term and hence no martingale. I've just put the old formulation of what the ST dynamics were, showing that there was a deterministic component, and now we've removed that under our new Q probability measure. So we can safely say that ST over BT is a Q martingale because it's normally distributed and the expectation stays the same. So the expectation of that ZT measure that we've just found, that random Nigdum derivative, is actually equal to 1. So just highlighting that even further, we've got our change here, our transformation that we've made to that WT term. So you see we've just added that alpha dt, the deterministic component, and we determined that alpha was equal to mu minus R over sigma over the volatility, which is actually what we call this market risk parameter. So now if we actually substitute that dw tilde t into our dynamics formula in the top right hand side there, you can see that we get the change of the Brownian motion dynamics from the physical probabilities to the new risk neutral probabilities. And you can see here now that our stock price is actually RSTDT instead of mu. So I'll let you substitute the DWT in, rearrange, and then get this formula here. But now this is our new stock dynamics under the Q probability measure. So now we get into the crux of it. Why do we do all that? Well, essentially, you don't need it when you're trying to value European call and put options, because it's really well defined by the Black-Scholes formula. However, when you get into more complex derivative pricing, for example, the payoff's complicated, or there's some certain contract features that require you to, look at the value of the process over the time of that option. Well, then you actually have to get into something more complicated, and this is where the risk neutral expectation pricing formula really comes into play. So I wouldn't expect you to be using it every day like we just have to look at the stock dynamics for the Black-Scholes model, but as soon as you start getting more complicated, that's when this process really comes in. So remember, from the basics, we can actually construct a replicating portfolio of a stock and bank account with a value process VT. Now, what we're doing, remember, is we're just trying to replicate this VT process to the actual payoff of the option or the derivative over that lifespan. We did not prove it here, but the physical probability measure and the Q probability measure are equivalent measures. And what do we mean by that? We mean that they have the same sample space and they have the same set of possibilities. So they're equivalent measures. Now, for the Black-Scholes model, there is only one equivalent probability measure. If there were multiple, that would mean that we would have more than one fair value price for our option. So under the Brownian motion model, we actually have only one equivalent measure, Q. We've just shown that the discounted stock process, so ST over BT, is a Q martingale. So the expectation is equal to the value of that process beforehand. Therefore, any discounted portfolio of the bank account and the stock is also going to be a Q martingale. So what can we actually derive from this? Well, under the new probability measure Q, the discounted value process exists that is a martingale. So the discounted, I just have the value portfolio of the stock in the bank account divided by the bank account, right? Which is just that discounted process, E minus RT. So we have just proved that that is a martingale. From that, we can take from the left-hand side the discounted process of the derivative, and we can therefore say that we have the expectation of the discounted process of the payoffs given filtration is actually equal to the discounted process of this value process of the bank account and stock, this replicated portfolio. Now, that is extremely powerful because what we've just said is that any options or derivative price can actually be constructed with this replication approach, and we can use this risk neutral pricing under this Q probability measure, to actually value our derivative at any time. That's a very powerful statement. Said more clearly, more popularly stated with the bank account as the numere, you can have different numeres that you're actually investigating. But here, this is probably the most simple risk neutral expectation formula that you'll see. CT, the call option, divided by BT is equal to the expectation under that Q probability space that the call price, the call payoff at the end, divided by the bank account at maturity, given the filtration process. So what is special about this formula? Well, essentially, we can now use this to price many derivatives with respect to the bank account or the risk in a risk neutral world, and that is extremely powerful. As we start investigating more complex derivatives, as we start looking at different contract features, maybe we've got some time component that we're looking at, we can actually value this by simulating the risk neutral probabilities in the Q measure space and then taking the discounted expectation to get the value. And that is a very powerful methodology for high dimensional calculations that really comes into its own compared to the PDE approach and then having to solve high dimensional PDEs. So hopefully that makes a lot of sense. If you guys have any questions regarding the risk neutral expectation probability and things like that, please answer them, please just ask them in the questions below. And we're going to be delving into more now the application of this in Monte Carlo space. So we've gone through the boring mathematics, but it's quite exciting, the mathematics here that we can actually now apply to Monte Carlo simulations. So that's going to be the topic for the next couple of videos, and I hope you guys really enjoy it. So if you did enjoy the video, please give it a thumbs up, and I will see you in the next one.